Hi students, today we are going to discuss about Werner's theory of coordination compound. Swiss chemist Alfred Werner was the first one to propose a theory of coordination compounds to explain the observed behavior. Let us consider the different colored complexes of cobalt 3 with ammonia, which exhibits different properties and different color. Right. Next, Werner took some coordination compound. He added AgNO3 and he found different moles of AgCl precipitate with different colors. For example, he took COCl3 6NH3. By adding AgNO3, he got 3 moles of AgCl precipitate and the complex turns to yellow color. Right, 3 moles of AgCl, the complex turns to yellow color. Second, the COCl3 5NH3. By adding AgNO3, he got 2 mole of AgCl precipitate. The complex turns to the purple color. Right. The another case, COCl3 4NH3. By adding AgNO3, 1 mole of AgCl formed. Next, COCl3 3NH3. By adding AgNO3, no mole of AgCl formed. Based on this reaction, he derived structure of coordination compounds like this. He explained why he got different moles of precipitate through his postulate of Werner's theory. In this concept, I will tell later. Come to the postulate of Werner's theory. There are 5 types of postulate. The first postulate, valency. He took metal. The metal has 2 types of valency. The first one primary valency, another one secondary valency. The primary valency indicates the oxidation state of metal of cobalt. The secondary valency refers to the coordination number of cobalt. For example, COCl3 6NH3. Right. Here, the Cl3 is the primary valency. The Cl3 attached to the cobalt, this is the primary valency. 6NH3 attached to the cobalt, this is the secondary valency. Right. This is the primary valency. Here, how many valency is here? How many chlorine is here? -3. It is satisfied by +3 cobalt. Come to the structure. This is the cobalt is central metal atom. This is the primary valency. 3Cl, the outermost electron. This is the outermost electron. The NH3 is the secondary valency. How many NH3 here? 1, 2, 3, 4, 5, 6. So, coordination number is 6. Coordination number is 6. How can we identify +3 oxidation state? Here -3Cl. So, satisfied by +3. So, oxidation state is +3 because the oxidation state indicates the primary valency. The coordination number indicates the secondary valency. So, here the coordination number 6 is the coordination number. This is the secondary valency. This oxidation state +3 is the oxidation state. Cobalt is the +3 oxidation state. So, we call it as the primary valency. This is the first postulate. Next, we will discuss the primary valency. The Cl is the primary valency, we know that, right? Mostly positive and certain cases in 0, satisfied by negative ion, which means the primary valency of metal ion is positive in most of the cases, but certain cases only 0. They are always satisfied by negative ions. For example, in the complex COCl3 6NH3, the primary valency of cobalt is +3 and it is satisfied by 3Cl minus ion. Very clear? The primary valency maximum they are always satisfied by the negative ions. Right? The primary valency of cobalt is +3. The primary valency of cobalt is what? +3. This +3 satisfied by 3Cl minus ion. Next, secondary valency. The secondary valency is satisfied by negative ions, neutral molecules, positive ions or combination of these three. For example, COCl3 6NH3, the secondary valency of cobalt, not primary valency of cobalt. Here secondary valency of cobalt is 6, right? But here the primary valency of cobalt is +3. But here the secondary valency of cobalt is 6 because this is the secondary valency. The secondary valency indicates coordination number. Right? The secondary valency of cobalt is 6 and it is satisfied by 6 neutral ammonia molecules. 6 ammonia neutral molecules. Whereas COCl3 5NH3, the secondary valency of cobalt is 6. Right? The secondary valency is what? 6. The 6 is satisfied by 5 ammonial neutral molecule. One is left, right? That is 1 negative chlorine ion plus 1 negative chlorine ion. I will explain. Here the structure of CO, the central metal atom, is occupied the secondary valency ion 1, 2, 3, 4 NH3. This is the NH3. Right? This is the secondary valency ion. And third, primary valency ion. 2Cl satisfied by cobalt and another 1Cl satisfied by secondary ion. Right? So, whereas cobalt Cl3 4NH3 is satisfied by 4 ammonia neutral molecule and plus 2 Cl ions. Like this structure, you see this structure CO NH3 6 Cl3. This outermost electron only involved to the AgCl. To reaction with the AgCl to gives 3 AgCl. 3 AgCl turns to yellow color. Right? CONH3 5 and here Cl2 and 1 Cl come to inside the complex. The satisfied by cobalt plus 6. The Ag2Cl2 react with the Ag gives to 2 AgCl. It colors change to purple color. CONH3 4 Cl2 comes to inside. The Cl is the primary valency. The primary valency only involved to the Ag plus to gives 1 AgCl. According to this mole to gives color respectively. Right? Next, fourth one. The coordination sphere is 2 sphere. The first one is inner sphere, another one is outer sphere. This is the metal. This is the inner sphere. This is outer sphere. The inner sphere otherwise called as the coordination sphere. The outer sphere otherwise called as ionization sphere. Why we call it as like that? The inner sphere is closed packing to the metal. The inner sphere is closed packing to the metal. We can't split or we can't remove the ions from the metals easily. Right? They firmly attached to the metal. So we are call it as the coordination sphere. We know that already the coordination sphere cannot split, cannot give simple ions, only give complex ion. That's why the inner sphere is call it as the coordination sphere. This is the NH3, the 6 NH3. This is the secondary ion. This is the outermost electron, otherwise called as ionization sphere. Why we call it as ionization sphere? The electron occupied in the outermost electron easily remove from the metal. Easily remove from the metal. The chlorine is occupied in the outermost electron. The chlorine only involved to the reaction. Outermost electron only involved to the reaction. So we call it as this is the ionization sphere or outer sphere. We can't split, so we call it as coordination sphere, otherwise called as inner sphere. Right. For example, COCl3 6NH3. See the example. Cobalt, the central metal atom. Cl, 3Cl, primary valency. This is the primary valency occupied in the outermost sphere or otherwise called as ionization sphere. Easily removed from the metal because the distance is fair. Okay. Next. This is the NH3 is the secondary valency occupied in inner sphere or otherwise called as the coordination sphere. This is the complex form. We can't remove easily from the metal. Okay. This is the 2 sphere. Another one, directional. The primary valency or non-directional, while the secondary valency or directional. This geometry of the complex is determined by the spatial arrangement of groups. Spatial arrangement means the particular place which satisfies the secondary valency. For example, if metal ion has secondary valency of 6, the metal ion has secondary valency of 6, it has been octahedral geometry. It has been octahedral geometry like this. NH3, 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 NH3 here also. This is the directional. But primary valency Cl is occupied like this or like this. This is the non-directional. But secondary valency occupied the spatial arrangement of groups in particular position. Okay. If secondary valency is 4, it has either tetrahedral or square planar. This is the square planar geometry. This is the tetrahedral geometry. Maybe either any one tetrahedral or square planar. This 5 postulate of Werner's theory and the limitation of Werner's theory. Even though Werner's theory was able to explain a number of properties of coordination compounds, but it does not explain their magnetic properties, does not explain the color. Only he explained number of properties of coordination compounds, does not explain their color and magnetic properties. Thank you.